Hey, geometry students. In this lesson, we are going to be talking about something that is going to be a throwback to algebra. We're going to be talking about slopes and equations of lines. And yes, this is something that we learned a lot starting in Algebra 1, how to graph linear equations. Okay, so this is going to feel very familiar to you. I do want to point out that we've been talking a lot about Euclid and Euclidean geometry and how Euclid liked to work with just a compass and a straight edge. And he would draw these shapes and prove that different relationships about the shapes or different relationships between the shapes and other figures, he would prove that things were true very systematically. This would be very foreign to Euclid because when we talk about slopes, we're talking about measurement, rise over run, how far something goes up versus how far something goes over. And when we do that, we have to measure up and measure over. Euclid would not have done this kind of measurement. The idea of the coordinate plane or coordinate grid would be very foreign to Euclid as well. So it's important to realize that this is modern geometry. This is going to be the bridge between algebra and geometry. And even though this may seem familiar from an algebraic perspective, it's important for you to start to merge together your understanding of geometry and what a line is geometrically with what a line is algebraically. So let's get started. We're going to start off with the definition of what a linear equation is. And I hate the definition that's in our geometry book. The definition of a linear equation in our geometry book is an equation whose graph is a line. You might as well say an equation that is linear is a linear equation. It's a very reflexive definition, and I don't like it. So I added a little bit to it. From our text, our textbook says this, but it's not the definition. It mentions that the variables have to be first degree variables for it to be a line. So in our equation, we can have x, we can have y. As long as we don't have x squared, or x to the 1/2, or x to the 3rd, we're fine. X and y to the first power will make a linear equation. Now, I want you to think about this. Back in algebra, you probably only really ever dealt with linear equations in two variables, x and y. And you would graph those in a coordinate plane. Wait, a coordinate what? A coordinate what? What? It's a coordinate plane. The word plane is familiar from both algebra, coordinate plane, and geometry. What do you know about planes and lines in geometry? Well, you know that lines that are coplanar either have to intersect or they have to be parallel to each other. Well, guess what the two relationships between lines were in algebra when we graphed lines on a coordinate plane in x and y? We could have lines that were parallel to each other or lines that intersected each other. Technically, we could have lines that were dependent on each other, that were the same line, okay? But that's sort of a weird case because if two lines are the same line, can you even say that they're two lines? Or does it just mean that they're one line because they have the same exact equation? That's getting a little bit too philosophical for us. Can a line ever have more than two variables? Now notice it doesn't say with two first degree variables in this definition. It just says with first degree variables. What about if I had three variables, x, y, z? Then I have a line in coordinate space. And then I could have two lines that don't intersect and aren't parallel. Only if I have three variables can I have lines that are skew, because I need space for lines to be skew with one another. Okay, so in a coordinate plane x, y, I can only have lines that are parallel or intersecting. In space, which we never dealt with in algebra, if we did deal with it, we didn't deal with it in any kind of deep way where we were really understanding it. In coordinate space, x, y, z, I can have skew lines. There's another relationship that's available to me. There's one connection between algebra and geometry. This is what our equations for lines look like. Linear equations will always have x and y to the first degree, and that's the only qualifier. So I'm looking at these x's and these y's. This is x to the first, this is y to the first, bam, linear equation. X to the first, y to the first, bam, linear equation. Oh, what about this one? There's no y at all. This is embarrassing. Actually, what's going on here is I have a coefficient of 0 multiplying my y. You can picture it that way, right? So if I just have one variable to the first degree, that's also a linear equation. We're going to talk about this as one of the two special cases we'll talk about later. And then over here, oh, what if I'm dividing x and y? Certainly if I divide them by a number, they're not going to be linear anymore. Well, actually, they are linear because it's x to the first, y to the first. It is the only qualifier. Okay, if I have x to the first and y to the first, that means that it's going to be a linear equation. So this would be a linear equation with a slope just like all of the other ones. All right. We mentioned this before, but I'm just going to mention it again. Linear equations connect algebra, where we're talking about them as equations in x and y. Technically, they could be equations in x, y, and z if we wanted. And geometry, which is lines in a coordinate plane. Well, wait a second. Lines in a coordinate plane sounds very much like what we learned in algebra about linear equations. So this is the connection point. Lines exist both in algebra and geometry, and they actually mean essentially the same thing in both places. So it's kind of this cool logical bridge between the two subjects. All right, what is the rise of a line? The rise of a line is the vertical change between 2 points on a line. Point A, point B. Point A might be higher than point B. So I'm going to have a different vertical coordinate for point A compared to point B. How do I find the difference? Well, I can find the vertical coordinate, the y coordinate for point B, and subtract from it the amount of the y coordinate for point A, and that tells me the rise, the vertical change. I can do the same thing with run, the horizontal change. If I take the horizontal coordinate from one point and the horizontal coordinate from another point and subtract them, I get the change between the 2 points. We'll talk about why that equation that I just gave you is significant in just a bit. The slope of a line is the ratio of the rise to the run, the ratio of vertical change compared to horizontal change. It puts in one number, just one number, information about how steep the line is or how shallow the line is, okay? That's what the slope does. It's just a single number that tells us how the line changes as it moves across the coordinate plane. We can calculate the slope by dividing rise by run, and there's a really simple formula to calculate the rise and the run. The rise, as I mentioned before, is just the change in the y coordinates, so y2 minus y1. The run is the change in the x coordinates. It's simply x2 minus x1. And if I divide those, y2 minus y1 over x2 minus x1, that gives me the slope of a line. So all I need to find the slope are 2 coordinates, 2 points that are on my line. And that will allow me to calculate the slope of my line. All right, there are 2 special cases of slope that I mentioned before. One of them is a horizontal line. A horizontal line doesn't rise at all. It stays perfectly horizontal as it moves across a coordinate plane. That means that the rise of a horizontal line is always 0. And if I divide the rise by the run, if the rise is 0, that means that my slope is 0. Because 0 divided by anything, it doesn't matter how far over it goes, 0 divided by anything is 0. So the slope of a horizontal line is 0. Now, somewhat seemingly paradoxically, when I have an equation for a horizontal line, that equation is going to be y equals something. Wait a second, though. I thought y was the vertical. How could y equals 6 be a horizontal line at 6? Well, the reason for that is because if I say y equals 6, I mean y equals 6. That means y equals 6 regardless of what x is. Where's x? What is happening to x? Well, x is being multiplied by 0. Deal with it, okay? There is no x. In other words, it doesn't matter what the value of x is. It doesn't matter what the value of x is. It could be 1, it could be negative 100, it could be 1,000,000. No matter what x is, y is always 6 if y equals 6. And that's why I have a horizontal line at y equals 6. Because x can be anything from negative infinity to infinity, and y will equal 6. Same is true if x equals something. If x equals something, it's going to be a vertical line. X equals 3. I have a vertical line at 3. What if y is 1,000,000? X equals 3. What if y is negative 2? X equals 3. What if y is the square root of 5? x equals 3. It doesn't matter. Okay, so that's why if y equals something, it's a horizontal line. If x equals something, it's a vertical line. And if something's a vertical line at x equals 3, is a vertical line at 3, the run is 0. It doesn't go horizontally. So the run is always 0. If I tried to subtract a x coordinate from another x coordinate, I always be subtracting the same number from itself, which means it gives me a run of 0. And I can't divide by 0. Rise over run, if run is 0, rise over run is undefined because there is no value. How do I divide by 0? You can't divide by 0. So because we know that anything divided by 0 is undefined, the slope of a vertical line is undefined. All right, now time for a life hack. If you put an equation, and you can change around equations to change both sides and still have the same equation, right? As long as you do the same thing to both sides of an equation, we're cool. You can change an equation so that y is on a side by itself. Slope-intercept form is what happens when you get y on a side by itself in a linear equation. It's a way of writing linear equations that explicitly shows the slope and the y-intercept. And I mean explicitly here, like it makes it really obvious. I don't mean explicitly like the same kind of explicit that you see as a warning label on some music, right? The slope and the y-intercept are G-rated, okay? But they're also very clearly shown to you in slope-intercept form equations. You know exactly what the slope is just by looking at the equation. You know exactly what the y-intercept is. And because you can graph where the equation crosses the y-axis and the slope, the rise over the run, very easily, it's super easy to graph a line from its slope-intercept form. So get used to it. Because it's really easy to use. You want to make sure you keep using slope-intercept form. What is slope-intercept form? Y is on a side by itself. Okay, that's the key. Y is on a side by itself. Why is y on a side by itself? I don't know. I just wanted to say that. But y is on a side by itself. So the way that this works is if y is it has something added or subtracted to it, you need to use algebra and do something to both sides to get rid of that thing that's being added or subtracted from y. Notice y doesn't even have a coefficient though. It's not 3y equals mx plus b, it's just y. So if y is being multiplied or divided, you have to multiply or divide both sides of the equation and get y on a side by itself. Y has to be all alone on the left-hand side. And then the other side is mx plus b. Now why is this useful? Well, m, the number that's multiplying x, or could be dividing x kind of, but remember, all division is multiplication. It's just multiplication by a fraction. The number that's multiplying x is the slope, is the rise over run. It's the one value that tells you how high your line goes for how far over it goes. Or if it's negative, how low it goes for how far over it goes. B is the y-intercept. If I plug in 0 for x, I get a y point when x equals 0. If I plug in 0 for x, y equals b. So b tells you where your line crosses the y-axis. If b is 2, your line crosses the y-axis at 2. You can put a point right there at 2, and you know that that point is on your line. Okay, so the slope-intercept form is super useful. We're going to be using it in some practice problems we're going to be working in just a moment. So now you have reviewed a whole lot of information about lines, but honestly, reviewing is abstract, and this has been probably a little difficult for you to keep track of. So let's put some concrete in this, and let's actually do some practice problems in the next video. Please tune in and watch as we use these concepts to do some actual problems.